Okay, we are on almost the last video for the chapter, and the reason I say almost is because the next video will be your study guide video. Yay, we're almost done with this chapter. There are a couple exceptions to the octet rule that you do need to be aware of. The first one we've already discussed. Hydrogen only wants 2 electrons. The other exception is boron. It's happy with 6 electrons. Beryllium is happy with 4. So we have boron with 6, beryllium with 4, hydrogen with 2. And molecules with an odd number of electrons do not make typical Lewis structures. That one's really hard to read. I see that now, but I'm not going to go back. So I'll leave you to do this one on your own. It says nitrogen dioxide. Again, it's going to make an atypical Lewis dot structure, but I think you can do this one. So let me know how you do with nitrogen dioxide. Okay, now we're going to start talking about what to do with Lewis structures. And that's where this comes in. Valence shell electron pair repulsion, aka VSEPR. The reason we need VSEPR is the same reason we needed to know Lewis structures. Well, see, we needed Lewis structures so we could learn about VSEPR. But we need to understand how the molecule behaves, whether it's polar or nonpolar, because that will allow us to make predictions about its behavior and why Ralph, the polar bear, wouldn't get into water anymore after he took his chemistry class. The more you know about the shape of the molecule, the better predictions you can make about how the molecule behaves. So our steps are, first you got to draw the Lewis structures. Then we have to learn to tell the difference between bonding electrons and lone pairs, which you should already be able to do, and then read the table. And I'll let you know which part of that table you have to memorize and which part you don't. VSEPR is where we really start looking at what the molecule looks like. Lewis dot structures do not give us any clue about the molecule's shape at all. The shape is what determines the polarity of the molecule and its behavior, and Lewis structures do not do that. All Lewis does is tell us where the lone pairs are and where the bonds are. So let's put that down. Lewis shows only where the bonds are and where the lone pairs are. It does not do the shape of the molecule. Now, I know you're like, well, I got a molecule on my paper and I can see that it looks like a big old T or a big old X or something, but that's not really the shape. VSEPR is where we start being able to imagine this in 3 dimensions. So the first thing we need to look at is what we call 2 electron pairs. If you take a look, it's always going to be about this central atom. This guy right here, we're going to call it carbon because carbon's a good central atom. It starts with C for central, right? Well, C for carbon. But it's a good central atom. If the central atom has 2 electron pairs around it, they're going to be in terms of bonds. 2 electron pairs, and they have to be bonded. Now notice on this particular molecule, the central atom has no lone pairs. Everything about VSEPR is about the central atom. So if the central atom has 2 bonds on it, no lone pairs, the shape of the molecule is linear. And we say that the bond angle is 180 degrees. If you're asking yourself, yeah, but carbon only has 2 bonds on it and it wants 4 bonds, it wants 8 electrons, that carbon's not satisfied. You are totally right, and let me show you how that works. Okay, so carbon dioxide is a classic 2 electron pairs molecule. For VSEPR, key point, key, huge, pay attention, don't fall asleep on me, key point, these bonds, we treat multiple bonds, I ran out of room, multiple bonds as singles. So for VSEPR, when I say how many things are on the central atom, you can treat this as if it was 1. So there's 1 thing here and there's 1 thing here, which satisfies the 2 things on the central atom. So here we have 2 things on the central atom, no lone pairs, Booyah, the shape, linear. No lone pairs on the central atom. Remember, when I say lone pairs, in this particular picture, oxygen has a lone pair and another lone pair. So oxygen has two lone pairs, but it's all about the central atom. And in this case, there are no lone pairs. There's two things around the central atom. Therefore, it's linear, with a bond angle of 180 degrees. Now, when I say there's 3 electron pairs around the central atom, 3 electron pairs. When I ask you how many electron pairs are on the central atom, I'm talking about both bonded and non-bonded. Well, both bonded and lone pairs. So if you count the total things around the central atom, there better be 3 for this molecule. So in this one, there's 1, 2, 3 things on the central atom. There's no lone pairs. This is the shape of the molecule. It is trigonal planar. We say it's trigonal because there's 3 bonds, planar because they all lie on the same plane. Well, that's a really badly drawn plane, but they all lie on the same level. So that's why it is planar. Boron trifluoride is an example of something that would be trigonal planar. Boron in this case has 3 bonds on the central atom, no lone pairs, so the shape is trigonal planar. The bond angles of a trigonal planar arrangement is 120 degrees. Yes, you need to know the bond angle of both a linear and a trigonal planar arrangement. Now, sometimes with 3 electron pairs, remember when I say electron pairs, I mean both bonded and lone pairs together. Sometimes you're going to end up with 1 lone pair on the central atom, like this molecule. So take a look at GE. GE has 2 bonds. There's a bond here, and there's a bond here. But look, there's lone pairs right here. So on this particular molecule, the VSEPR arrangement, we say, is bent. It is not trigonal planar, it is bent. And the bond angle is a little less than 120 degrees. When there are 3 things, so by things I mean bonds and lone pairs on the central atom, the electron arrangement, or the electron geometry, we'll do that, geometry, is trigonal planar. However, the VSEPR arrangement, because of this lone pair, is bent. This is another good example. Sulfur has 2 things that are bonded, 1 lone pair. So if I were to add all this up, taking a look at sulfur, sulfur has 3 things around it. 1, I count this as 1, and I count this as 1. So that's 3 things on the central atom. The electron arrangement is trigonal planar, but the molecule itself is bent with a bond angle of less than 120. Another example is this one. 3 things on the central atom with 1 lone pair. Looking at a molecule with 4 electron pairs, things get a little more interesting. The arrangement of VSEPR with 2 electron pairs, 3 electron pairs, and 4 are the ones I expect you to know. So here we have 4 electron pairs around the central atom. This includes both things that are bonded and lone pairs. It is a 4-sided shape. If you look at the faces on the shape, now for a long time I thought tetrahedron, a tetrahedral structure meant because it had 4 bonds. Well, it does have 4 bonds, but really the name comes from the shape. If you take a look at the faces here, let me find my pen. Oh, you probably can't see the yellow on the white, so we'll do purple. Right here, there's a face. You can see that shape, and here there's another face here. It is a 4-sided shape is where it gets its name, and that's called a tetrahedron. So this 4-sided molecule's name is called tetrahedral. Go ahead and say it. It's fun to say, tetrahedral. Again, this is a tetrahedral shape. If the central atom has 4 things around it, either bonds or lone pairs, the electron geometry is going to be tetrahedral. But then again, so's the molecular geometry. Methane is a classic 4-sided shape. It has 4 bonds. All of the bond angles are 109.5 degrees. Yes, you need to know that. Its shape comes from the faces of the tetrahedron. The electron geometry for methane is tetrahedral. The molecular geometry for methane is also tetrahedral. Because there's no lone pairs on the central atom, both the geometries are the same. Things are more interesting when you have a lone pair on the central atom. On this particular example, notice the central atom has 4 things around it. It has, I'm going to choose a pen color here, use green. It has 3 bonds on the central atom, plus this huge space of lone pairs. Because the space on the lone pairs, it like pushes down on these. It's like, you know, I need more space here. I'm going to squeeze you guys just a little bit. And so the bond angle actually becomes less than 109.5. You don't need to know the exact number. It doesn't matter. But the electron geometry, because there's still 4 things on the central atom, it starts off as tetrahedral. But because there's 1 lone pair on the central atom, this molecular geometry we call trigonal pyramidal. And you can see that this shape down here kind of resembles, I can't draw 3 dimensions, kind of resembles a pyramid. And these shapes are easier to see if you're doing this, you know, you take the tetrahedron, shape the molecule with little balls, and you take the lone pair off, you can see the trigonal pyramidal shape. Again, this is pretty much the same thing. This is the trigonal pyramidal shape. It's not showing the lone pairs. If I were to show the lone pairs, it would look more like this. And your bond angle on this would be less than 109.5. Ammonia is a classic example of what we're talking about. Nitrogen has 3 bonds on it with 1 lone pair. The electron geometry then is tetrahedral because there's 4 things on the central atom. However, because there's 1 lone pair, the molecular shape ignores the lone pairs and it becomes trigonal pyramidal. And the bond angle is less than 109.5 degrees. Water is a classic example of a bent molecular shape. If you take a look closely at water, oxygen has 2 bonds and 2 lone pairs. I couldn't resist. The electron geometry is tetrahedral because there's 4 things on oxygen, the central atom. However, because of the 2 lone pairs, the VSEPR structure, the molecular structure, we say is bent. Because those lone pairs take up so much space, the bond angle then is less than 109.5 degrees. Still looking at water, notice the four things on the central atom. We have two lone pairs, one there, two bonds. Four things around the central atom automatically makes the electron geometry tetrahedral. But because it has two lone pairs, the molecular shape ignores the lone pairs, and we end up with a molecular shape that is bent and a bond angle of less than 109.5 degrees. The previous slides that we saw, I do expect you to know on the test what the electron geometry and molecular geometries are based on the Lewis structure. This point forward, you would be allowed a table to help you out for these, because these structures you will encounter. Knowing this stuff without a table is something I would ask at the AP level. If there's 5 electron pairs around the central atom, whether they're lone pairs or bonded, doesn't matter, the shape of this molecule is trigonal bipyramidal. If you notice, it has 3 sides. I can't see the one in the back, but the top makes a pyramid. The bottom makes a pyramid. Each pyramid has 3 sides. There's 2 pyramids, so it's trigonal bipyramidal. If there are no lone pairs on the central atom, then the molecular geometry is also trigonal bipyramidal. The bond angles on this are 90, and then these, see how that's 90 degrees? These are all 120 degrees. The atoms that form a straight line, these guys right here, will never, ever, ever be where what the lone pairs end up. Your lone pairs will always be either here or here or here, because the arrangement of the atoms wants to keep things as far apart as possible, and this 180 degrees does the trick. They're called axial atoms. The ones around the side are called equatorial atoms. No, you don't really need to know that for Gen Chem. Take a look at this molecule. It was trigonal bipyramidal. However, it ended up with a lone pair. The lone pair would sit right here, one of the equatorial atoms. Because it has one lone pair on the central atom, the molecular shape is seesaw. See, can you see the seesaw? This guy would, oops, one of them would go down, the other one would, I gotta go back. There we go. This guy would go down, this guy would go up, and they could play seesaw, and these guys sort of stabilize it. But that's the molecular geometry. It kind of makes more sense if you actually get the little balls out and build it, and you can actually see it looks like a seesaw. This is a classic example, sulfur trifluoride. Sulfur has 2 lone pairs on the central atom. So if I'm counting the things around both bonded and lone pairs, we have 1, 2, 3, 4, 5 things on the central atom. That means its electron geometry is trigonal bipyramidal, but the molecular geometry we call seesaw. Just another picture of the same thing. Notice the lone pairs are sitting right in the equatorial atoms, just like I promised they would be. Bond angle there is 90 degrees, and those bond angles are 120 degrees-ish. This is our T-shaped molecule. It came from an electron geometry called trigonal bipyramidal. It had 2 lone pairs on the central atom, and its molecular geometry is T-shaped, and sure enough, it looks like a T. This is a classic example, well, not a classic, this is just a different picture of how this would look. And here we have chlorine trifluoride. Here is a lone pair, here is a lone pair. You can see the trigonal bipyramidal shape of the electron geometry. However, with these 2 lone pairs, we say that the molecular shape is T-shaped. Don't worry about knowing the bond angles. The last shape for this 5 electron pairs would be if the electron geometry starts out as trigonal bipyramidal And here we have, ooh, that's a typo, not 2. We have 3 lone pairs on the central atom. The electron geometry, the molecular geometry, rather, would be linear. The most interesting one to look at is the one with 6 electron pairs. When there's 6 electron pairs, the shape is called octahedral, which is like sort of mind-blowing because 6 is not octa, right? Remember, the name comes from the shape, and as you can see, this is an octahedron. There are 8 faces on this shape. If there are no lone pairs on the central atom, then the molecular geometry agrees with the electron geometry, and it's called octahedral. This is a classic example of an octahedral structure. Sulfur, let's see, 1, 2, 3, 4, 5, 6, yep, thought so. Sulfur hexafluoride. More simplified example of the structure. Again, this is not something you have to know. You would be allowed a table to read this. Now, if the electron geometry starts out as octahedral, and you have 1 lone pair on the central atom, then we say the shape is square pyramidal. As you can see, I've put a square pyramid on here. So you can see what a square, see the base is square. Base word, oh yeah, there's the base is square, and the shape forms a pyramid. That's where it gets its name. Now, what do the atoms look like? Take a look at this structure. It doesn't matter what the molecule is, we've just used strange names. Remember, we never ever touch the axial atoms. But we have 1 lone pair on the central atom. 1 lone pair on the central atom. I don't know why that lone pair is there, but that's okay. But look at the shape. There's the square, there's the pyramid. Because all of the electrons are equidistant, you don't really have an equatorial atom, so it doesn't matter where you place it, because everything is 90 degrees apart. So here you have your square, there you have your pyramid. So the molecular geometry is square pyramidal. Would you be allowed to have a table for the test? Yes, as long as you're not an AP. Here's another example. If there are 6 electron pairs around the central atom, then our geometry will always be octahedral. But if there's 2 lone pairs on the central atom, then we say the shape is square planar. And that's what a square planar looks like. It's all on the same plane. This one I like just because it shows that even though the molecule is square planar, these 2 blue atoms do have some extra atoms hanging off of them. But the central atom is what gives it its shape, and it is square planar. This is a space filling model, shows the same thing. I kind of like the ball and stick models better. Now, if there's 3 lone pairs on the central atom, the shape is T-shaped. Four lone pairs on the central atom means it's linear. Okay, this is a summary of everything we've done so far. If there are 2 things on the central atom, there will never be lone pairs. Can't do it. So this shape will always be linear. The bond angle will always be 180 degrees. Yes, that's something you need to know. If there are 3 things on the central atom, bonded or not, the electron geometry will always be trigonal planar. And your bond angles are 120 degrees. But if you have 1 lone pair on the central atom, it is bent, and the bond angle then is less than 120 degrees. If you have 4 things on the central atom, bonded or lone pairs, the electron geometry will always be tetrahedral. Oh, we should put the bond angles here, 109.5 degrees. If you have 1 lone pair, the shape becomes trigonal pyramidal with a bond angle of less than 109.5 degrees. With 2 lone pairs, it's bent, and its bond angle is less than 109.5 degrees. The ones for the 4, 3, and 2 you do need to know. I expect you to be able to do those without a table. The 5 and 6 I do not until you're at the AP level. If there's 5 things on the central atom, it is called trigonal bipyramidal. 1 lone pair means the shape is seesaw. 2 lone pairs gives us T-shaped. 3 lone pairs, oh, that's not on there, but 3 lone pairs then would be linear. A 6-sided structure we call octahedral. I know that's strange, but it is octahedral. 1 lone pair gives us square planar. 2 lone pairs, oh, I said that wrong. I was looking at somebody else when I said it, but that's okay, because you can read a table for this one. But if you look up here, 1 lone pair gives us trigonal, gotta get the words fixed up. 1 lone pair gives us square pyramidal, that's square pyramidal. 2 lone pairs gives us square planar. Good news is you do get to use a table for those. 3 lone pairs is T-shaped. And lastly, 1 lone pair is linear. What do you need to know? You need to know these. These other guys I'd let you read a table for. Yes. The best thing you can do for VSEPR structures is to practice. First, draw the Lewis structure, and then build the molecule to really see what it looks like in 3 dimensions, which is why the next thing I have for you is a practice worksheet. That's it. Have a great day.